turn our attention to continuous functions defined on a real interval. Let's start with a plain definition. Zero of a function is a value that the value of the function is zero. For example, uh, let's say function as x is equal to 2x minus 2, for example, and uh, a zero of a function is a value that turns this function zero is equal to zero. Find the zero of the function. We equate this function to zero, and x will be equal to 1. Then if 1 is the zero of a function, there are some conditions that helps about telling the condition of the zero, even the function of a zero exists, and even with this condition, we even somehow determine the number of zeros. The theorem is this. According to the theorem, if in a closed interval between a and b, if we find that if a and multiply by if b is less than 0, then the function has at least one zero. To visualize this, let's plot a graph. Let's say that if a is this point, it's negative, and if b is in this point, and we see that if it's continuous, it has to pass from, for example, let's say this type of function, it has to pass from 0. Then it at least has a 1 0. Okay. Why we say at least 1 0? Because it can also go like this. In this function, for example, it has even 0 zeros, but at least it has 1 0. And by this theorem, we can see that if a can be bigger than 0 and if p can be less than bar, or if a can be negative and if b can be positive to hold this condition. But there are important noticeable there are important notions that we have to know about this theorem. First, without continuity of the function, we can tell that it has a zero or not. The continuity of the function is actually very, very important. For example, let's say in an interval, in 0, 1 interval, there is a sine function, and of course, if the function this interval, and of course, this function is not continuous, and um, in the graph, so we can see that there isn't any zero function. In sine function, it will be like -1 or 1, and because it is not continuous, but right there, more clear, because this function is not continuous, then we can't say that it has a zero. Actually, it doesn't have zero. Secondly, the function can have a zero without requiring this condition. What we mean, for example, fx is equal to minus 2 square. We can see that actually the function is positive for all real values except one. When x equal to 2. In x equal to 2, it will have a 1, 0, but we can see that in other values, it is also positive. Actually, fa multiplied by fp condition doesn't hold for the interval of 0, 4. It is because it's always positive, but it has a 1, 0. And also need to mention that by this theorem, we can also somehow approximately find the zero of the function. For example, let's say that x is equal to minus 1, for example. We can see that for x0, the value is minus 1, and for 1, the value is 1. As we know from the theorem that we learned previously, this function will have at least one zero. But we can somehow try to approximately find this zero. For example, it is minus 1, right? Then we can increase this value a little. For example, f 0, 0.5 will be equal to 0 square plus calculate this. No, wrong. It's just and when we calculate, find that plus and 3 multiplied by find this square, and this is this, and we will find 3 divided by 60, and 3 divided by 16 minus 1 will be equal to this. Then as we can see, this value is less than this. Uh, and I forgot to mention, this function is polynomial, then hence this function is also continuous. The continuity is very important condition for this theorem. We need to always consider it. And let's 0.8, I put a little bit. Minus 1 equal to let's simplify this. This to simplify, we will find each by using to express proof quickly. This is 8, and as we can see, minus 8, minus 29, right 5, uh, and as we can see, this value is also bigger than this. Then we are approaching the correct value, and eventually we can find this value. Uh, but let's work more. This seems actually uh, yeah, and calculate it. Zero, one, final zero, zero. This, this, and here we will multiply it by this value, and we will find 0.10 plus 33 by it. This, 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 this. 8, 3, 2, 5, like this. Interestingly, um, we found approximately 0.5. Then we need to decrease the value a little bit, and eventually we will probably find the zero of the function. But this value will be approximate, not the entire value, not the total correct value. There are other corollaries coming from this theorem. For example, uh, um, let's say there is a two function uh, in an online closed interval AB, and these functions are continuous, and for A, FA is bigger than FB, and FB is less than not FB. FA is bigger than GB, and FB is less than not GB. FA is bigger than GA, and FB is less than GB. The contrary also will hold. Then there is at least some point that these functions will intersect. For example, to visualize this, let's say that FA is like this. Well, let's say GA, the G function is like this. This is the G function. And let's say this is the F function. As we can see, the FA is bigger than GA. This is A point, and GB is bigger than FB. And there is a point that they intersect. It is kind of natural. I don't see any reason to explain this. Watch just a closed and bounded integral. Uh, let's say that m is the minimum of the function and m is maximum of the function. If the function is continuous on the interval b, consequently, a will be equal to will be between m and n. This is very understandable. For example, this is the in the interval. This is this g function. This point, GA point, is the minimum, and m is the maximum. As we can see, the all points are between m and n. We can easily see that there isn't any point, for example, jumping from to this. If was there any point, it will be maximum function. But if it isn't, uh, then all points are included in this interval. So there is another theorems. Also, one important theorem tells that if the function is strictly monotone, for example, there is a function, if it, if and only if it is strictly monotone, then this is the one-to-one function. If, for example, it isn't strictly monotone, it is like this, then it is not one-to-one, and as a consequence, it will not have a inverse. There is another theorem tells that if b if interval f is continuous and interval there is also one theorem that I want to mention, and actually this is very important theorem. If the function is continuous and invertible, then the inverse of the function will be continuous. Why it is important? Because we by this theorem we will find the inverse of the we will find that actually the inverse of the function is also as a derivative. We will use this function to for this purpose.